Welcome to this presentation. I'm Dario Santonocito, a postdoc researcher from the University of Messina. This work is entitled Fatigue Damage Assessment in IM Polymers Evaluating Their Energy Release. This research activity is part of the collaboration between the University of Messina and the Norwegian University of Science and Technology. The aim of this work regards the investigation of the fatigue properties, adopting full-field techniques such as infrared thermography, of polyamide 12 specimens manufactured with selective laser sintering printing process. The mechanical properties of the material were evaluated, and the temperature trend of the specimen's surface was monitored during static tensile and fatigue tests, applying the static thermographic method and the thermographic method. In particular, the static thermographic method is proposed as a rapid test procedure able to correlate the temperature trend to the fatigue properties of the material during static tensile tests, adopting a very limited number of specimens. Thermography has been used as an aid for assessing the fatigue properties of several kinds of materials. As observed by La Rosa and Risitano, if we cyclically test a material with a stress above its fatigue limit, the temperature evolution of the specimens monitored with an infrared camera is characterized by three phases. An initial rapid increment in the first phase, then it reaches a stabilization temperature, and finally, in the third phase, a very high further temperature increment until failure. Generally, the higher the applied stress, the higher the stabilization temperature, but on the other hand, the subtended area of the temperature number of cycle curve could be assumed constant and related to an energy parameter phi. If we report the stabilization temperature versus the applied stress, the fatigue limit of the material could be defined as the intersection with the stress axis. In addition, if we stress in a stepped way the material and we evaluate the energy parameter and their different stabilization temperature, it is possible to obtain the number of cycles at which the material will be broken if we cyclically test with that stress, hence obtaining the SN curve. The static thermographic method has been developed during the last 10 years. The first paper by Risitano and Risitano was presented in 2009. In 2013, Risitano and Risitano proposed the static thermographic method as a rapid procedure to derive the fatigue limit from a tensile test. During static tests of common engineering materials, the specimen's temperature is characterized by three phases. An initial approximately linear decrease due to the thermoelastic effect following Lord Kelvin's law. Then, in the second phase, the temperature deviates from linearity until a minimum, and finally it experiences a very high further increment until the failure. If it is possible to estimate the stress at which the temperature trend deviates from linearity, that stress could be related to a critical macro stress which is able to produce in the material irreversible microplasticity. This critical stress is the same stress that, if cyclically applied to the material, will increase the microplastic area up to produce microcracks, hence fatigue failure. The material under study is a polyamide 12, which has high mechanical properties, good chemical resistance and biocompatibility. A set of 6 specimens was produced by selective laser sintering, an additive manufacturing technique that adopts a laser beam to sintering plastic or composite powder. The specimens were produced according to the geometry prescribed by the ISO standard, with a nominal cross-section of 10 per 4 mm, adopting the EOS commercial powder PA 2200. The specimen's building orientation angle was of 0 degrees respect the X machine direction, allowing a volume internal grid-like structure due to the orthogonal laser beam trajectories. Two kinds of tests were performed adopting a servohydraulic test machine. Static tensile tests on 3 specimens adopting a crossed speed of 5 mm per minute. Stepwise fatigue test applying the thermographic method on 3 specimens with stress level increase of 1 and 2 MPa, 3000 cycles per block, a stress ratio of 0.1 and test frequency of 1 Hz. During static and stepwise tests, the specimen's temperature was monitored with an infrared camera with a sample rate of 1 image per second. Static tensile tests were performed on 3 specimens of Pi12 obtained by selective laser sintering process under displacement control. The adoption of an extensometer allowed to obtain the engineering stress-strain curve of the material. The curves exhibit the same trend, with an initial linear elastic part followed by a smooth hardening, where it is not possible to assess in a clear way the yielding point. To evaluate the Young modulus, the linear regression of the stress versus strain between the indicated strain values has been performed. As it's possible to see in the table, the evaluated Young moduli are lower compared to the value of the material datasheet. The specimens exhibit an ultimate tensile strength lower compared to the value of 48 MPa reported in the datasheet. On the other hand, the elongation at break is higher compared to the nominal value of 0.24. In the same table are reported data for the same material from literature. The different reported values of such 3D printed material show how its mechanical performance are severely dependent on the printing parameters. During static tensile tests, the evolution of the specimen's surface temperature has been evaluated by means of an infrared camera. The applied stress is reported versus the specimen's surface temperature variation, estimated as the difference between the instantaneous temperature and the initial temperature of the surface recorded at time 0. The temperature data has been filtered with the air loss filter with a data span of 5% in order to reduce the outliers and highlight the thermoelastic trend. In the initial part of the temperature time curve, it is possible to clearly distinguish the linear trend of the temperature, then it deviates from the linearity, reaching a plateau region. Suddenly, it experiences a rapid increment. It is possible to draw two linear regression lines, the former for the first linear phase and the latter for the second phase, not taking into account the temperature values near the slope change. Solving the system of equations, it is possible to determine the intersection point of the two straight lines. The corresponding value of the applied stress could be related to the macroscopic stress that introduces the first microplasticization phenomena in the material. While test 1 and test 2 show the same temperature trend with a gradual transition between phase 1 and phase 2, the second one has a more marked transition with a value of the limit stress considerably lower than the others. The average limit stress for the three considered tensile tests is equal to 24.4 plus minus 3.5 MPa. Static tests with a stepwise increase of the applied stress level have been performed on 3 specimens with a stress ratio of 0.1 and 1 Hz of frequency. During the test, the superficial temperature has been monitored with the infrared camera. For each stress level, it is possible to observe and estimate a stabilization temperature. For the last stress level, no stabilization has been reached and the temperature increased until the specimen's failure. Moving from 24.5 MPa to 26.4 MPa, a higher temperature increase is noticed, hence the fatigue limit of the material falls within this range. If we report the different stabilization temperature versus the applied stress level, it is possible to observe two linear trends with different slope. The first linear trend is typical of stress level below the fatigue limit of the material and can be addressed to noise in the temperature signal or material damping, while the second is characteristic of energy release due to fatigue damage phenomena. By the intersection of two linear trends, it is possible to assess in a very rapid way, even with one specimen, the fatigue limit of the material. The value of the limit stress found with the static thermographic method is in good agreement with the one of the fatigue limit found by thermographic method. The limit stress is a more conservative fatigue parameter compared to the fatigue limit for a positive stress ratio of 0.1. Compressive loads are a more severe fatigue damaging condition for the specimens. After static and fatigue tests, the fracture surfaces have been evaluated through an optical microscope. In the left figure is reported the fracture surface of a specimen failed during static tensile test. The fracture surfaces show a ductile failure with very limited plastic deformation. A series of defects is clearly visible due to the lack of powder melting. The defects have a circular shape with an average diameter of 0.175 mm. Fatigue fracture surfaces show a smoother profile, typical of a brittle failure. Defect due to the lack of powder melting with an average diameter equal to the one of the static cases have been found. The circular defects can act as an initiation site for plastic deformation that would lead the specimen to failure, both under static and fatigue loads. In conclusion, in this work, the energy released during static tensile and fatigue tests on specimens made of PA12 by selective laser sintering process has been evaluated. The infrared camera allowed the application of the static thermographic method and of the thermographic method, monitoring the specimen's surface temperature. By the static thermographic method, the average value of the limit stress has been evaluated as the stress level at which the temperature deviates from its linear trend, obtaining a value of 24.4 MPa. By the thermographic method, the fatigue limit has been evaluated as the first stress level for which higher stabilization temperatures are observed. Its value is equal to 26.5 MPa. The limit stress is in good agreement with the fatigue limit, and it is a more conservative fatigue design parameter. For additive manufactured materials, given the strictly dependence of the mechanical performance with the process parameter, it is necessary to evaluate the fatigue properties in a very short amount of time and with low material consumption. Hence, the static thermographic method and the thermographic method can be a useful aid. Thank you for your kind attention.